yesterday, and we looked at the frequency versus the length of a string, right? What did my graph look like? Okay, so it looked like some 1 over x relationship. So then we decided we were going to linearize it. So what did we do? Yeah, so we looked at the frequency versus 1 over L. And what did my graph look like? It was a straight line business. So yay, we proved that it was some 1 over x relationship. So now I want to look at we're going to have a little thought experiment. So what if I this time leave my length constant, whereas yesterday we changed the length, but today I decided to increase my tension. What would that do to frequency if I increased tension? Yeah, it would increase frequency. So F will increase as the force of tension increases. Alright, so second thought experiment. I'm going to leave L constant again, but this time I want to increase the string thickness, or the mass per unit length. So if I increase this mass per unit length, what would that do to my frequency? It would decrease. So F will decrease as mass per unit length increases. And this mass per unit length is actually denoted with a mu. So now I've studied a couple of factors that could affect our frequency, and we still can't put them into an equation yet, but we can make this proportionality, okay? So I've looked at the length, I've looked at the mass per unit length, and I've looked at the force of tension. So where would my length go? Is it directly or indirectly related? Indirectly, okay? So what about my tension? Is my tension directly or indirectly related? Directly. So what about my mass per unit length? Indirectly, okay. So we're on our way to making an equation, but I want to look at the units here for a minute to see if we can end here, which we can't, but we're going to prove why, okay? So what are the units for frequency? Hertz or seconds? Or, yeah, inverse seconds. Good. So if I take what I have going on up here, so I have the force of tension over the length times the mass per unit length. So what is tension measured in? Newtons. Okay. And what is length measured in? Meters. Okay. What about mass per unit length? Kilograms per meter. Good. But what is a Newton? Yeah, a kilogram meter per second squared. Yeah. All over meters times kilogram per meter. So if we make that a little prettier, we get something that looks like this. But I can cancel out our kilograms here. So then we're left with meters squared over meters times second squared. And so this is where I'm going to do something we don't normally do. I'm going to square root things because I'm trying to prove what the equation is to you. And I know you don't generally just square root things in the middle of an equation. So just thought experiment. What if I square rooted these things? Okay? So I'm going to square root the meter squared, and square root the seconds. Okay? So then I have, what, a meter over a meter times a second. What is that? It's an inverse second. So it's frequency. That's what I want, right? So I'm going to go back up here, and I'm going to look at my equation here that I have, and let's see what I have. Force of tension, and then we're going to square root him, right? And length times this mass per unit length, and I'm going to square root him, okay? Because we just decided that would help us get the right kind of units, yeah? So we're now going to say that this is the square root of tension divided by this mass per unit length divided by length, okay? Are we all good so far? Alright, so I want to look at the units, though, of this guy right here. So that's what? The square root of the force of tension over this mass per unit length. So without the square root for a second, I have force of tension over mass per unit length. So what kind of units do I have? Newtons over a kilogram per meter. Yeah? So, and what's a newton? Kilogram times meter per second divided by kilogram per meter, which gives me what? Kilogram, meter, get squared, times, meter over kilogram, yeah? I'm going to get rid of my kilograms again. And what am I left with? M squared, over second squared, okay? So, but I decided up here that this whole term is going to be square rooted. So, if I square root this, what am I left with? Meters per second. And what is meters per second? It's the speed, yay! Isn't that cool? So now I can change my equation that I've been working with. So now it's what? V over L? Yeah. Okay. So, but I'm still not done. There's still some parts of this equation that the old sciencey guys decided were important. So we're going to take this and we're going to compare it to a couple of different standing waves and see if we can decide what the entire equation is. So just as a point of reference for what we're about to do, we're going to call this one wavelength, okay? And what was my equation for velocity as it related to the frequency in the wavelength? Maybe frequency times wavelength? So amplitude times omega, yes, but we're looking for this equation. And if I rearrange that, I get frequency is equal to velocity over wavelength. But does that look familiar? Does that look similar to maybe this up here? Yeah? V over L, and then I have V over lambda. So I'm going to say that our lambda and our length are equal. Okay? So do y'all remember the other day when Miss Howell had the slinky out in the hallway and she started talking about the first harmonic and the difference between all the nodes and antinodes, yeah? So this is where that's going to become important. So I want to look at this standing wave. How many nodes does this wave have? 2. 1, 2. So how many antinodes does it have? 1. So this is what's called the first harmonic. And if we use this up here as a reference point, how many wavelengths do I have in this first harmonic? If half, yeah. So if this is a whole wavelength, this down here would be half of a wavelength. So then maybe wavelength is equal to 2L, yeah? And if I put it into my frequency equation, I would get V over 2L. Alright, so I'm going to move on and we're going to look at the second harmonic because I want to see if I can find a pattern here. So what if I have this right here? How many nodes and how many antinodes do I have? How many nodes? 3. 1, 2, 3. Okay, how many antinodes? 2. So this is the second harmonic. Alright, so if we compare this picture up here to our reference point, how many wavelengths do I have? How many wavelengths is this? 1, yeah. So that would then make our frequency equation just V over L. Alright, so I'm going to look at one last harmonic and see if maybe I can come up with some kind of pattern. Alright, so how many nodes do I have here? 4. How many antinodes do I have? 3. So this is the third harmonic. Alright, so how many wavelengths do I have here? 1.5. Good. So, and I can write 1.5 as 3/2, yeah? So that would make my wavelength equal to 2/3 L, which would then make my frequency equation V over 2L. So I'm going to take the 3 equations that I just made. Let's see, we have this one, and this one down here, and we're going to compare them and see if we can come up with some patterns. Do you notice anything similar about any of those 3 equations? Particularly the first and the third? 2L. They both have a 2L on the bottom. So what if I were to add in a 2 here and a 2 here? So that didn't really change the equation because 2 over 2 is still 1, which is still V over L. But now do all of these equations look more alike? Yeah. So, and what if I put a 1 here? Do we notice any pattern on the top of these equations? 1, 2, 3. So it's the number of the harmonic that it's in. Yeah? So if I wanted to write an equation that I could use all the time, it's maybe F sub n, so n being the number of the harmonic that we're looking at, is equal to n V over 2L. Alright, so what if I wanted to compare that to the equation I was looking at the beginning of class from our lab, right? So I had F is equal to 1, proportional to 1 over L, right? But now I've added in some other business here. So I have N for the number of harmonics, and then this velocity, but what was the velocity? The square root of something? ft over this mu, and then divided by 2. So do we see that if we looked at our graphs, because I can now put an equal sign here, if I was looking at my graph that I did in the experiment from yesterday, you think maybe I could find what my mass per unit length is? Yes? So these waves, when you made a wave by flicking that string yesterday, what harmonic was it in, do you think? Did it wave around, or did it just go like up and down? Just went up and down. So maybe that it's in the first harmonic. Yeah? So then if I looked at all this stuff, I know what my tension is in my string because I used 300 grams, right? Yeah, of mass. I used a constant mass. So we would have 3. Ooh, it's a big square root. Do you think, and I knew the length of my string, or the lengths that I was changing, you think maybe I could find my mass per unit length from our experiment yesterday? Yes? Okay.